Still right, perfect. Yeah, my name is Thomas Weible from FlexOptix, and I got the honor to have now a presentation, the last final session, about a really hardware-related topic. So imagine it's all about about building a network, and when you want to build a network, the smallest unit you have two nodes, and the challenge is, if you want to connect those two nodes, you need components, building blocks, especially like cables, fiber optic cables, or even RJ45 cables. And you need transmission units, and that's the talk about mainly, about transmission units. Don't get afraid, it's a little bit high school physics, nothing much more. These transmission units look like this. This is an optical transceiver. Tiny, nice shape. And the great thing about this one, this is for example an SFP Plus, which is a small form factor pluggable. It was agreed by a couple of vendors and manufacturers to say, well, we want to have the same dimensions, the same physics, and also the same electrical interface, because we want to have them interoperable. And these people call themselves the multi-source agreement. Some people also say it's a standard, but it's not an official group saying that it's a standard. So it's an agreement that these modules, which are used as a transmission unit, have the same housing and electrical interface. What do I do within FlexOptix? I'm a co-founder there, and also day by day I work with transceivers, look into the innards, and that's what I'm going to show you now. So when we rip up a transceiver and look inside, there are a couple of components, and I'm a little bit colorblind, so I need a green one. There are mainly three parts in there. We got the electrical side, which communicates with our host and gives back to our router or switch what kind of transceiver is plugged in, what kind of capabilities this transceiver has. The second component is a microcontroller unit within the transceiver, which stores all that information, but also has some other function. It does control the optical engines or the optical component, which are a receiver and a transmitter. And that's also where this artificial world transceiver is coming from. It's transmit and receive combined, and you get a transceiver. That's basically it. On the MCU, I'm going to talk at the end of that talk, but for now we stick to the receiver and transmitter, and we take two important things or of optical characteristics of a transmitter and a receiver. But before I jump in, it's really important to know what is light. So light is basically, we have a really great light source, which everyone knows of us. We don't see it now, but it's the sun. Here we have artificial light, and light is measured in nanometers. The light which our eye can see as a receiver, and the sun is the light source, or these artificial light bulbs here, is measured in nanometers. And what we can see is in a spectrum from 400 nanometers, which is blue light, up to 800 nanometers, or almost 800 nanometers, which is red light. For a transmitter, it's a little bit different, or a transmitter in optical networks, it's a little bit different. We start basically at 850 nanometer for a 10 gig SR application, and go up to 1600 nanometers for colored CWDM, but more later there. So that's really one important thing. The laser or the transmitter matters what kind of light is emitted, what kind of color of light is emitted from that laser. And the second fact is, or the second important thing about optical transmission systems is the receiver side. The receiver has a really nice capability, similar like our eye. Our eye can capture all kind of light, a broad spectrum, and an optical receiver can also do the same. It can capture a broad spectrum of light and detect the signal in that spectrum. So starting from, for example, from 1260 nanometer up to 16 nanometer, 1610 nanometer, it can capture all the light and still detect the signal. And these two characteristics, so that our transmitter can be really precise what kind of light is emitting the transmitter, and our receiver, which is for the broadband, is really important now for the upcoming slides, and also why transmission systems are working the way they are working today. So that's a setup which I'm pretty sure everyone knows. You use it day by day, and the reason why it's working, it's pretty simple. You get a transmitter on the left side, and you get a fiber, and this transmitter is, for example, emitting orange light, and this orange light is hitting the receiver on side A, on side B on the other side, and it's going to be detected. The same happens from side B, the transmitter emitting light over a second fiber, getting to the receiver on side A, and we got a link, we got a span, and the data can flow from A to B and B to A. Pretty straightforward. Now, when we think about what I said before on the previous slide, we have a transmitter which we can really be specific on the light which he is emitting, then we can reduce the amount of fibers. We can only have one. How does this work? We have a transmitter still with emitting orange light going through that fiber, but now instead of hitting the receiver directly, it's going to hit a filter. The filter is similar like sunglasses you put on when you look into the sun, which you shouldn't, but it just filters a certain amount of light out, even a certain spectrum. The same does an optical filter, so it only allows, this filter here on side B, only allows the orange light hitting the receiver. The receiver doesn't care, because it can take all kind of colors. It's a broadband receiver. On the other side, we got the green light now, and that's different compared to the previous light. We got a green light going through that fiber and hitting a green filter. And that green filter, again, only allows the green light going through to the receiver on side A. Now, that's pretty straightforward. We got filter, we got green and orange lasers. But why does this work on a single fiber? And that's the great thing about waveforms. Waveforms which you have in the ocean, for example, or wave on audio waves, and the same applies for light. They don't interfere with each other, so they overlap, but they don't influence each other, and that's pretty cool. So we can put them on the same media without interference each other. Now, moving forward and think, okay, we only have two colors now, we can extend this. And Paul yesterday mentioned it already in his talk. It's a little bit like when it comes to technology called coarse wavelength division multiplexing. It's a little bit like slicing up a rainbow, and that's basically it. So on the bottom line, we see 4 different kind of wavelengths, but within that window we can have up to 18 wavelengths, so starting from 1270 nanometers up to 1610 nanometers with the spacing of 20 nanometer each. And the great thing here is it gives us the ability to add more applications on a single pair or even on a single strand of fiber. With coarse wavelength division multiplexing, we do have for example, 18 times 10 gig on a single pair of fiber. And if we tweak the laser even more, we get to dense wavelength division multiplexing, and that's shown on the top. So you see that the area where we are talking, starting from 1528 nanometers up to 1561 nanometer, is even more narrow, but the lasers are even more precise. So within this range of 30 nanometer only, we can fit in up to 80 channels, so 80 channels. Thinking of 10 gig applications, 10 gig Ethernet for a single channel, this will end up in 800 gigabit. Which is doable in terms of the DWDM setup, but there is another story talking on layer 2 or layer 3 enabling link aggregation doing 80 channels. That's a different story and not covered by that talk. But from the background, what enables CWDM and DWDM it's all the same what I mentioned before. First thing is we have a precise laser with a defined light emitting out of that laser or transmitter, and we have a broadband receiver can capture all kind of light, and we do have filters which allows us to go pass through only a certain type of light, and that happens for CWDM and also DWDM the same. So this filter at the beginning here on a bidirectional communication, it's the same for CWDM. We have for every single color a dedicated filter, and for DWDM with the 80 channel the same. So this will end up in 80 filters, or for CWDM 18 filters. Now that's one thing when it comes to the application point of view for transmission systems, that we got the receiver, the transmitter, and the other point is we come to form factors. And the first form factor I introduced at the beginning of that presentation is the small form factor pluggable, but there are other form factors out there as well to enable your application or to enable your links between different devices. And it's mainly an evolution of time when the first form factors were developed. And here as an example, I took the 100 gig form factors, which are available since 4 years approximately, and the first one is the big box here. It's a CFP, and just as to compare this in the analog world, the CFP has approximately a size of an iPhone 6 Plus, and it uses a lot of power, up to 30 watts. I don't think iPhone 6 Plus needs 30 watts, but a CFP does. And with the time, this working group for the CFP improved the technology in there, got to the CFP2, you see it's half the size, and then moved on to the CFP4, even again half the size. In parallel, there was another working group working on a 100 gig form factor, which is the QSFP28, and this is the same people developed in the past the SFP form factors, and now they developed the QSFP28 form factors. As you can see, this one was developed way later than this one, so this guy is approximately 3 to 4 years old and since 3 years available on the market. In the middle, I missed one thing. It's a CPAC. It's also a 100 gig one, but it's really proprietary, and it was difficult for me even to get a picture of that proprietary one. Only one vendor used it, so it's not really an option when it comes to use transceivers in different type of systems. Looking at the form factors, this gives also a good picture on the current market, what we see out there. We had yesterday the talk from Andrew about basically all ports are 10 gig ports now. There's no 1 gig any longer. I see the same picture. I don't have 10 gig on my slide either. But let's start at the latest stuff. So currently 400 gig is in development. I haven't seen it physically yet or personally yet. And oh yeah, there will be new form factors coming out. So the mess keeps on going. There is a form factor called QSFP28 double density. It's the same size of a QSFP28, but even more lanes coming in there. And a new one is introduced in OSFP. We will see what's going to be in there. You also see something interesting when you look at 200 gig transceivers coming up. Also a new form factor, CFP8. So it's even new development there. And here you see that the CFP family is always ahead in development. So they have the big advantage, this working group. They can consume more power, they can dissipate more heat, and they have bigger sizes available. And on the, that's great, but it's even more complex. So when you look inside a CFP, it's way more complex than a QSFP28, for example. These start to become available now. But the mature technology for 100 gig is QSFP28. It's available, it's there, and if you want to deploy 100 gig, it's based on QSFP28. It has really a nice port density. At the talk from Attila today, we heard 100 gig ports. This will end up, for example, in 32 100 gig ports on 1U. That's pretty nice port density. And for 10 gig, the SFP Plus is that's the form factor I introduced at the beginning. That's the form factor which is running in high volumes, which is cheap, available, and doable. And finally, I don't want to talk any longer about XenPack. And for XFP 10 gig, well, they are still around, but I haven't seen new installations based on XFP because all major vendors building line cards now even have SFP Plus based line card to doing 10 gig. Yeah. So we got the optical components as a criteria for transmission system. We got the form factor depending on what kind of application you want to do, and then and what I didn't say it explicitly, but these transceivers have the nice benefit they are pluggable. And from that MSA's working group, they had the intention that those pluggable modules can be interoperable in different systems. So we have the same housing, we have the same electrical interface, we want to plug them into different systems, but there's still that microcontroller in there which needs sometimes a little bit to be tweaked, that it's gonna be, that it allows the host to recognize the transceiver, basically. And that's the third component, compatibility. That's where we specialized in, and therefore we developed the Flexbox. It's a tiny device, a USB device with different form factors, starting with QSFP28 or SFP Plus down there, up to CFP and CFP2 and 4. Making it possible to change the microcontroller inside of a transceiver to be compatible from one host, and also taking that transceiver out and plug it into another host system, being more compatible. We do this quite successful in the last couple of years. We have more than 40,000 compatibilities available with a small crowd of people, only around 40 people. And well, there's some new things going on at FlexOptix, but let's leave space for the next SAFNOC and not for now. Thank you very much. Are there questions? Who is still awake? No? All right.